guess someone was saying half the class dropped out, so is that the case? I don't know, we'll find out. Okay, so I circulated the first problem set, so hopefully you saw it. There is also a programming one coming, so this one is just all kind of conceptual stuff, covering pretty much everything we have done thus far. Last time I had started looking at some of the complicating issues that come up when we do scheduling, and so today's goal is to kind of wrap up that discussion and then move on to the next topic. But if you recall, some of the things that we had covered were firstly, what if tasks shared resources? And one of the key takeaways from last time was that as a result of resource sharing, what may end up happening is that a resource is used by a high priority task and a low priority task. And if the low priority task grabs the resource, then high priority task has to wait for it, and somehow we have to account for that. So there is a there is an interference that occurs because of low priority tasks, which we have to account for when we look for the response time. And a further complicating factor was that other tasks may also get affected. So if there is a task in the middle, and a low priority task grabs a resource that the high priority task needs, so unless we do something careful about it, this medium priority task may keep coming again and again and prevent the low priority task, which has the resource, from running, and then the high priority task can wait for a long time. So we saw priority ceiling protocols to deal with that. The second issue we had looked at was that the way we defined priorities are based on the timing characteristics, whereas the other notion of priority is the criticality or the importance of the task. Now, when there is a situation where there is an overload, that is, some deadline has to be missed, then the lowest priority task will miss the deadline, but that may be a safety critical task. And so we saw this concept of splitting the tasks such that the two notions of priority, importance and timing, are kind of aligned. So what you would want is that if something has to fail, then it's the less important task that should fail. And the reason why we enter into overload situation are multiple. Processor can basically slow down unexpectedly. There may be other cross traffic on the link, on the processor, and you can think of analogous things for communication links and such. So that was the next issue that we looked at. Another issue that we had looked at was what happens if tasks feed data to each other. And so what ends up happening in this thing is there's usually a cluster of tasks which forms some sort of graph, and the first task in that graph, the root task, arrives periodically, triggered by some event, and then everything else kind of cascades, but it has to wait for the preceding task to finish. So, that and to do that, basically, kind of, I mentioned that it's kind of a hard problem. So you basically resort to kind of heuristics to make it happen. And one final thing that we had looked at was, let's see, so task with shared resources. Oh yeah, and another one we had looked at was uncertainty in execution time, and this happens naturally in the sense that many algorithms exhibit natural variation in execution time given the input value of for different values of the input. And so we had looked at two sort of concepts to cope with it. One is approximate algorithms, that is algorithms that you can stop in the middle and they'll give you some result, or if you give them more time then they'll give you a better result, and so on and so forth. And we had also looked at another strategy to cope with this thing was the notion of having alternative algorithms, so kind of a high quality algorithm which on an average does fine, but under certain input conditions can take a lot of time, and then we have a backup strategy which is kind of a quick and dirty thing. So that's another way. And there are other strategies you can also imagine to cope to do with this kind of stuff. Another approach could be right at the beginning you do your quick and dirty thing so that there is a result out there which meets the deadline, and then in the remaining time that you have, you try to do your backup algorithm. So variety of approaches, but they are all dealing with this issue of uncertainty. So we are going to continue with this these issues. Another one is that rarely nowadays are systems kind of just standalone systems. So usually data are produced on one network node, sent over some sort of network, consumed at another one, and then perhaps sent again, and so on and so forth. And these networks in some cases may be wide area networks. So we nowadays have sensing and control done over the internet, and even at home or a single building, there are lots of different delays that you might encounter. Very loosely speaking, anytime you have a network, you have to deal with propagation delays and you have to deal with queuing delays. So propagation delay is just time of flight for the bits to take, and queuing delay is that at variety of intermediate nodes, packet may face a delay to be processed because there was other traffic there. So all of these things kind of take away from this clean abstraction that we were assuming, which is things are periodic, because a task running on a processor, if it is being triggered by some arriving event, and if that event is arrival of a packet, then there is going to be sort of jitter on it. So one of the challenge that we face out here is that if you think in terms of like arrival of a sensor input and then finally some action being done on it at some actuator, that whole computation pathway is no longer on a single processor. It's kind of split across multiple processors and communication links. And yet you have to meet kind of a deadline. So very first thing that happens is somehow you need to divide up your delay budget, the allowable end-to-end delay along these different nodes. Some of them may be under control of different parties. So for example, let's say you take a cell phone. Okay, so we speak at our cell phone, kind of goes through the base station and the network, core network, and then the other base station, and then comes out. And all along the path, variety of different processings are being done. And yet there is a end-to-end requirement that exists on this delay just because of human perceptual quality. So usually on cell phones and all, you're probably looking at maybe a couple of 100 millisecond type delay, after which round-trip communication or whatever interactive conversation becomes very painful, because if it's like 200-300 millisecond from me to you and another 200-300 millisecond from you back to me, then the chances that I'll be speaking over you will cutting each other and all increase. So a good rule of thumb is that. Then the question becomes, how do we allocate? How much delay should my handset have? How much delay should base station? How much delay in the core network? So just that problem of dividing end-to-end deadline into deadlines for subsystem is a pretty challenging problem. Again, intractable, no clean answer to it. You also need to deal with the fact that not only there is delay, this delay is time varying. So one packet may reach very quickly, the other packet may reach relatively, may take a longer time. So a strategy to cope with it is to put a buffer. So if you have jittery traffic and yet you are assuming some sort of a clean periodic abstraction, then you put a buffer, and you take stuff out from that buffer on a periodic basis. How much do you think should the length of such a buffer be? So let's say I have some events arriving, and these events are supposed to be periodic, but they actually are jittery. Okay, so because they're subjected to different delays. Intuitively speaking, what do you think will dictate the length of the buffer that I put on the receiver to smooth the traffic out?
Length of the delay?
Yeah.
The length of the delay?
Nope. See, if it's just length of the delay, then all I'm going to do is increase. It's going to be related to the variation in the delay, right? So just imagine, right? I mean, if the packets are arriving with perfectly deterministic delays, then it doesn't really help us. I don't need buffering, right? Because all that's happening is if the source was periodic, and if to every event I add a constant delay, then I still have periodic, okay? Other way of interpreting the delay might be I'll add the longest delay, right? Okay, so you could say that, okay, the packets being sent to the link, sometimes the longest delay they can take is, let's say, an hour, okay, and the shortest delay they can take is, let's say, 59 minutes, okay. Then adding 1 hour delay doesn't really buy us anything again. It's going to be sufficient, but it's unnecessary, because really it's the variation and the delay that we have to cope with, right? Because so the buffer in that case will be order of a minute, okay. So this variation and delay is something that if you can keep track of, then you can kind of, or if you know, then you can budget for that buffer on the receive side. But once you have a buffer, you are adding a fixed delay. So jitter in effect ends up hurting your latency, right? In this process. So in places where latency is important, you do want very tight control over the variation in a delay that are being encountered, in addition to, of course, the absolute delay that would come into play.
So in cases where latency is important, can I not just skip all the packets that have a very high delay?
You could, but then what if they are packets which are important from a perceptual perspective? They may carry important data. So you're right that you can imagine many application-specific strategies, right? I mean, so one is you can say, look, I'm going to wait for the packet, this buffer, but what if a packet probabilistically experiences even longer delay? Then I don't have the packet. So I can skip it, I can interpolate, kind of do some sort of guess, perhaps repeat the last value. So sensor data tends to be highly correlated, so you could make use of that fact. So this whole missing data problem can be addressed by a variety of ways, right? I mean, let's imagine it's a sound clip, right? If the packet didn't arrive, then the user will hear, and I don't play it, then the user will hear kind of some sort of noise. Or alternatively, I can seek to predict it based upon what was happening, and may have something smoother there. In case of a video, maybe repeat the frame, or maybe interpolate between kind of the next frame that arrived. So one can imagine doing a variety of things there. Certainly, there are no guarantees in communication, right? I mean, packet may never arrive, or arrive after such a long delay as to be useless. So eventually you have to be prepared that a packet may not arrive, and therefore take some graceful failure action. So one problem that we face in this networked setting is that we have to divide our end-to-end delay into allocation of delays for each link and allocation of delay for each processor. And then you could say, okay, and now I can go ahead and run kind of the same type of schedulers that we talked about for each one of the processor and also for each one of the communication links. But then you have to first solve the problem of splitting the deadline. So the other related issue that you face is before you can even do that, you also have to figure out how do you assign computation to the processors. So if I give you a bunch of processors and you have a bunch of tasks to do, where will you run them, right? I mean, one possibility is I assign all of them to a single processor, and but then maybe I will not have enough capacity to be able to do it. So is there a clean way we can think about this partitioning problem? So in general, implementation then boils really down to two things, and they're interlinked, right? One is that if I look at the set of tasks I have, and they may be sharing resources and they may be talking to each other, and I have a bunch of processors. I have to first figure out which task runs on which processor, and then I have to schedule each one of these processors and meet kind of some end-to-end deadlines that may exist. So this assignment problem and the scheduling problem, unfortunately, are interlinked in the sense that given an assignment, I can do a good scheduling, but then that may not be the best scheduling. So I may have to go back and revisit my assignment. So the two are interlinked, and but usually in heuristics, you're going to solve them in some order and then kind of iterate on them. So typically, for assigning tasks to processors, you may resort to some heuristics. So it could be that I have plenty of horsepower and I could rely on, remember from a couple of lectures ago that we had learned that if the processor utilization is less than what? Anyone remembers? For rate monotonic to always work? ln2, right? So if I have plenty of horsepower, then maybe I could put assignments, put tasks into these processors so that each one of them is ln2. I'm guaranteed scheduling, okay, and now I can deal with, and then I could just go ahead and do rate monotonic. But generally, but that may not be the best situation because again, I may have additional complicating factors like my communication link may have delays, they may have bandwidth constraints, all of these. So this placement of or partitioning of computation onto the physical resources and yet meeting deadlines, I mean, all these different facets of the problem are interlinked, but you could start with some sort of processor utilization based approaches or one common class of heuristics. So oftentimes it may simply be I have a set of tasks, I have to schedule them. Maybe I'll say, okay, let me start with the biggest task, put it somewhere, look at the next biggest one, okay. Variety of different goals, like one common goal maybe often is I try to keep the load balanced across the different processors, okay. Go ahead.
Like if you have, let's say you have a board that has Wi-Fi, Bluetooth, and Zigbee, some other protocol, and then you have large packets coming through Wi-Fi and some small data packets coming through Bluetooth. So how would you decide like which tasks to allocate which, because you do not know at what order they are coming?
So, okay, so the problem here that you're talking about is assignment to the board, okay? So maybe the constraint you're referring to is if I have a task which consumes Wi-Fi packets, then it cannot be arbitrarily assigned. It will have to sit on something where it can listen to Wi-Fi signals. So there may be additional constraints on the tasks which limit. So kind of step back and let's abstract the issue, right? I have a system with a bunch of hardware resources, bunch of platforms, okay? They're interconnected. These platforms have some sensors, actuators, some compute capability, some memory and all. I have some tasks. So that task in general would need some of the resources. Maybe this task needs the camera. So then it can only go on the nodes which have the camera, right? And then this task has some computation time. So it can only go on, a hard constraint, it can only go on platforms which have sufficient compute power to be able to do it. But even once you have that, so now imagine a simpler scenario. I have a bunch of tasks, they can run on any of the platforms. Okay, let's say the platforms were identical, a whole bunch of Raspberry Pis and a bunch of tasks. How do I split it among them? If I put all of them into a single Raspberry Pi, they won't work because it's too much computation. Processor utilization is greater than 1. So I have to split them out. And so the question here simply is, how do I split them out? And the challenging thing is that the tasks are often very uneven in size. Each one of them will have their own C's and T's. So I can't just arbitrarily pack them. And depending upon how you pack them, you are going to see different kind of latencies. And so kind of usually the design process out here is kind of an iterative one. You first try to come up with a mapping based upon some heuristic. Then you try to check whether this will work or not, whether this meets the deadline or not. And if not, you kind of go back and revise. The problem is each one of these two problems are intractable. Okay, so you have to rely on heuristic. In fact, even checking whether a particular assignment of tasks on a set of processors, interconnected processors, meets the deadline is basically requires exhaustive search. Okay, so and I'll show you why. So by the time you hit this level of problems, essentially we are in the world of heuristics, and there are gazillion different ones. So like for allocation, as I was saying, a very common class of heuristics is based upon processor utilization, which is I have a set of tasks and I kind of essentially start maybe with, let's say, the biggest, put them on one processor, takes the next one, put it on another processor. Common goals are try to keep the processor utilization to be uniform. So kind of intuitively, the idea is that if I pack everything on one processor, then scheduling might be harder. If I distribute the load, then I would be better off. And a whole bunch of other heuristics that kind of exist because there is no sort of theory there. Essentially, it's an optimization problem. You are trying to, you can think of it, so a lazy person's approach to these kind of problems is the following. I can make these problems as what are called as integer linear programs. Okay, how many of you have heard of linear programming? Okay, so good. Integer linear programming is basically where the variables can only take integer values. How many of you have done ILP, integer linear programming? Smaller number, okay. Now, how can I formulate? Let's take this problem. Let's say I want to formulate this problem into an ILP problem, okay? Let's say my goal is simply, for the sake of argument, that I want the tasks to be distributed on a bunch of processors such that no processor utilization exceeds 0.69 and number of processors are minimized. Okay, let's say a very simple version of this. So what I could do is for each task and each possible processor, I can define an indicator variable, variable which takes just value 0 or 1. So I can basically say that if task number 10 is put on processor 5, then the corresponding indicator value, let's say I5, 10 is going to be 1 or 0. So I have n task k processors, so n times k indicator variables. Each one of them could be 0 or 1. But now they are constrained. A task can go only on one processor. So I will create a linear constraint corresponding to that, saying that the sum of all the indicator variables for a particular task have to add up to 1. And they have to actually add up to exactly 1 because the task has to be mapped someplace. Okay. Then my utilization constraint. So the sum of the weighted indicator variables for all the tasks on a particular processor has to be less than 0.69. So that way I can capture the utilization constraint. And so I can list all of these things and then feed it to your favorite ILP system, ILP optimizer in MATLAB, or there are a whole bunch of open source stuff in Python and all floating around, and run them, and voila, you're going to come up with the solution. And for reasonably large size problem, this works fine. I mean, not for humongous problems, but the kind of things you're going to encounter. The only challenge is that they're probably not going to be fast enough to run in the inner loop of an operating system. But if you are, let's say, designing a chip or something, that's great. So very common approach, and it kind of forces you to think about what how to formally think about the underlying problem. But still, since this is slower for larger things, so there is utility of having heuristics as well. Now, deep down, these tools that do ILP, they are also solving an intractable problem, and they have heuristics, except that they have good general purpose heuristics that they have developed over time, which work for a large category of problems. So these kind of problems, you could do the ILP way, works fine for a lot of stuff, or for when you are dealing with larger scale systems, or when time is of an essence, then some sort of heuristic comes into play. Now, yeah, go ahead, Akash.
So coming back to like the sitting on a buffer, or we already know what tasks will be coming?
Task is just a piece of code
Right.
which is activated when the event that causes it to start arrives. Right? So what is a task? A task could be do filtering on sensor samples, right? Or and maybe the sensor samples are coming from a sensor which is on a remote node, and these are packets coming over a Wi-Fi. So in which case, this task is waiting for a Wi-Fi packet of a certain port, and whenever that packet arrives, we call the function, finishes, goes back. Next time the packet arrives, so it's these events. So task is, remember I had the notion of instance of a task and a task. A task is whatever, task number 10. It happens every time interrupt 5 happens, right? And so what's happening is every time the event happens, there is a instance of this task which is activated. It processes the data, finishes. Then again, the next instance.
But all the allocation that we're doing, that has like some way we are factoring in, basically the system can look into the future, like what all tasks will be coming, and then we do the.
No. Again, remember, task is just a piece of code or pieces of code, right? So if I have 10 tasks in the system, I have 10 functions, okay? And I tell the operating system, if I'm running task number 5 on processor I, then on to the OS on process I basically say, hey, here is a function, create a task out of it. Okay, and then what the OS, and by the way, this is the event of interest. So what the OS will do is every time that event happens, it calls this function.
Follow-up question, this allocation happens dynamically, or it happens when you compile?
So it doesn't happen when you compile the code, because compiler has no knowledge of other tasks, right? So so the question is still a valid one. Is the set of tasks static, or is the set of tasks potentially dynamic? Most systems, which are most of these operating systems that you see, they at some level do support dynamic, because the tasks are created by some call to the operating system, right? So you will start out at the very beginning of your program, you would say create this thread, create this thread, create this thread, and by the way, these are the functions associated with these threads, okay? So you are making it dynamically. The issue is that when are we checking the schedulability? When are we checking whether this set of tasks are going to run? You can do that beforehand a priori, because you know that I'm only going to create 5 tasks. And then you can do paper and pencil analysis and do it. Or alternatively, the OS can do it. Every time you call the OS to say, create this task with these values of T and C, and the OS can check whether this new task plus the previously created task, would they continue to meet the deadline or not? And at some and the OS kind of returns a success failure return value. So when you say create this new task, and by task here I mean create a thread with an attached function and values of T and C, then the OS can come back and say I can't schedule it, okay, at some point. So you keep creating things. There are systems where the set of tasks may truly be unbounded and dynamic. Imagine, for example, I don't know, let's say a system doing processing of targets in a radar, or like an air traffic control system, right? Every time it sights some flying object, it creates a new thread which is going to track that object. So now a system like this, if I organize it so that one thread or one task is created every time there is an object that enters into the field of view, then the number of tasks is potentially unbounded, because there might be many targets coming in. For each one of these targets, what may be happening is that the radar gets a new bearing, a new location on this on this particular target every second. So every second, some sort of an event will come, and the corresponding task is going to be activated again and again and again. So that's what we are calling as instance. So the jargon that I've been using is task is like a fixed entity, responsible for doing something for a series of events that are arriving. Okay, So when we so if the set of tasks are known a priori, you can do the whole scheduling, whole schedulability analysis. Is it going to work or not beforehand? And then somewhere in your code, which is fixed, you'll say create task number 1, task number 2, task number 5, and then I'm done. I'm not going to create any more tasks from now on. But the other is a more dynamic, fluid situation where somehow the number of tasks could potentially be unbounded, and in that case, the OS has to be super careful. The kind of most of the embedded systems you deal with, the set of tasks is usually known a priori, and therefore you can do all the analysis beforehand, not strictly in the compile time, but you can think of them as kind of compile time when you're before you start running the system, is how I would put it. Okay, so who does that analysis is manually, some sort of static tool, or the OS at runtime. Okay, all three possibilities exist depending upon how dynamic you want to be.
Because so my understanding was that suppose in the case of an Arduino, when you compile the code, there is one is yours, the initial everything, and then you have the loop component.
Mm-hmm.
So like when you compile it, somehow the Arduino board knows that whatever is inside this.
Okay, so firstly remember, Arduino makes no promises about anything.
Right.
Okay, so there is no analysis of schedulability that it does, or it's not making any promises about meeting any sort of deadline. Okay, but let's say were it to. Okay, so now what is the Arduino model? Okay, how many tasks are there in Arduino? And you have programmed, many of you I'm sure have programmed Arduino, right? I mean, there is an initial setup, and then it goes into a loop, right? What's happening in the loop? Well, it's essentially an infinite loop, and it's doing stuff, and then it has a third thing, which is the interrupt handlers, and there are interrupt handlers can send some sort of messages to the main loop. In this particular case, there is only one task, the one which I started out with. So essentially, you can think of Arduino as a following piece of code: setup, while one, loop. That's all it's doing, right? So those two functions. So in that case, it's literally one task, and now the question becomes that what kind of deadlines and all is it obeying and all? Well, you'll have to kind of do this analysis, which was very similar to when I had introduced foreground, background, and single program controller and all. There is no rate monotonic, there is no static priority, there is no notion of tasks in the sense of RTOS is too. Okay. Now, Arduino style of programming, you can certainly do within a single thread, within a single task. So you could imagine that on Linux, let's say, you can write a program which looks like Arduino. It has calls a setup function and then goes into a loop and calls and then loops through a body. And then that whole process, while it is running, is scheduled in and out by the operating system. If that was the only process on your computer, then it will always have the CPU, but if not. So I don't think comparing with Arduino helps here much, because it will only add to the confusion, because it's a very different model. There are no tasks there. What we are talking about here is more similar to threads in a regular full-blown operating system. Is probably the best way of thinking about it, because Arduino, no, yeah, but they don't have any OS, there are no tasks. Okay. Excuse me. So think of now, so one way of thinking that how the tasks that we are talking about get mapped into a real OS would be the following. You can think of tasks are mapped to threads, except those threads have a very particular structure. At the very beginning, the thread has something like wait for an event. And then once the event comes, it calls a function, f. And when the function finishes, it goes back to wait for the event. Okay, so let's imagine all my threads look like that. Wait for an event, call the function, go back to wait for the event. Now, that function is what I have been referring to as a task. That's That's one way. Now, of course, threads let you do a whole bunch of other stuff and all, but in this a very simplified view of the static priority model is the way I've been describing it is that. Now, in reality, it could be a lot more complicated. In a thread, I don't have to have wait for event just in one place. Maybe I can have other places where I'm sharing resources, like I could say wait on a semaphore and stuff like that. So there might be other places in the body of the thread that I may be blocking to. But think again about like the example I had. Whenever sensor data arrives, I want to do something. So whenever sensor data arrives, I'm going to process it, I'm going to send it over the radio, and then I'm going to wait for the next sensor sample. So I can write this piece of code as wait for sensor sample, do the processing, wait on the semaphore for the radio, send the result out, release the semaphore, go back to wait for the sensor sample, right? So the code could look something along those lines. Now, all these things can, in a simplified view, map to the abstract structure we had. That is, there is a task which has a period. So that period is really the external timing constraint. Every time the sensor sample arrives, it has a computation time, which is a computation time of this function. And if you have shared resources, then the stuff we talked about last lecture, kind of bring them in. So it's kind of your job, so to say, to map across these two worlds. But what it usually helps us to be disciplined about programming. If you think of your code in a structured manner, then that mapping becomes kind of easier to accomplish. So I don't know, hopefully that helps, but if it doesn't, just okay. So so at the high level then, I have a set of tasks which you can think of them as functions which are triggered when a corresponding event arrives or corresponding data arrives, and I'm basically mapping them onto processors. So a bunch of tasks go onto one processor, another set of tasks go to a different processor, and then at each one of them I let a static priority scheduler run, and my hope is that I meet the deadlines that I'm given. So this is, each one of these two steps is hard. So allocation is hard, and I described that how ILP could be used for it. What about this feasibility? So I claim feasibility is hard. What I'm saying is, even if I give you a mapping across multiple processors, the challenge is just checking whether the deadlines are being met or not is hard. You can't just simulate and claim that it works, because your simulation may not cover all the cases. Okay. Now, why it is hard is because it behaves rather unusually. So let's take the following. So on the left hand side, I have a system which have 5 tasks, P1 through P5, and there are some dependencies among them. So P1 produces data that are used by P3 and P5, and P2 produces data that are used by P4. And so you can think of them as, I have kind of 2 clusters. P1, P3, and P5 will have the same period, because every time P1 runs, and P3 and P5 have to run, and likewise P2 and P4 will have the same period. P2 runs, produces data, then P4 runs. So for every one run of P2, there's one run of P4. Okay, and likewise for every one run of P1, there's a run of P3 and P5. And I gave you, let's say, 3 processors, processing element 1, 2, and 3. There are many different ways I can partition these 5 tasks across those 3 processors. And then as a result, some of these data communication edges are going to go over the interconnect between these processors. How the processor elements are connected is a separate story. You can think of them, they're all sitting on an Ethernet, or maybe they just have dedicated communication links, whatever. Let's imagine we have this particular mapping, that P1 and P2 are on processing element 1, P3 and P5 are processing element 2, and P4 is on processing element number 3. So, and then on each one of these processors, I am going to do static priority assignment. So I'm going to look at PE1 and I'll say, oh, I have P1 and P2, let me give them priority and run a static priority scheduler on it. and likewise on P2 and P3 is just one task. Okay, so I will also have deadlines on these. So usually once you are given the task graph, your deadlines would be from the initial event that triggered P1 to when P3 and P5 ought to finish. And likewise, when the initial event triggered P2, P4 has to do some action. So it could be P2 reads some sample and P4 controls some actuator. So I will have a end-to-end deadline on that. And since P2 and P4 are on different processors, so now this deadline spans the spans across two processors. Now let's look at a simplified scenario where we can say, look, communication doesn't cost us any delay. So that's the easy situation. And but the computation time of these P1 through P5 are not necessarily fixed. Okay, and let's see what that results in. So let's say so it turns out that this problem that I give you this proposed partitioning, and I simply ask you a question that if you were to do rate static priority scheduling on each one of these processors, and I give you a set of deadlines, does this thing meet the deadline? It turns out that that problem is NP hard and pretty. So our older strategy when we were on a single processor, when we could just simulate our way out of it, doesn't really work. You have to do an exhaustive simulation in general. So why does it happen? And again, kind of just a simple example before I kind of make the broader point around it. So let's take a simpler task set. So now I have only four tasks, P1, P2, P3, and Px. And P1 is period of 100, Px has a period of 100, and P2 has a period of 100. Remember, they are part of the same cluster, so they'll have to have the same period. P3 has a period of 150. And then let's say the computation time, P1 is 10, P2 is 10, P3 is 30, but Px can take anywhere from 25 to 35. Okay, it's a contrived example, but we saw that computation time can have uncertainty. In general, all of them could be uncertain, but let's just focus on this being uncertain. And let's say I have mapped P1, P2, P1, P2, P3 on processing element number 1 and Px on processing element number 2. Okay, so P1, P2, P3 are on one processor, Px is on a separate processor. So now if I'm going to look at processing element 1, I will see that there are three tasks there, P1, P2, and P3, with periods of 100, 100, 150. So our prior theory suggests that P1 and P2 should be higher priority and P3 should be the lowest priority. Processing element 2 has a single process, so just one task, doesn't really matter. And let's say I have a deadline on P3. Okay, P3 should be 45. That is, so P3 arrives every 150 and has a relative deadline of 45, and it needs computation time of 30. So if we have that, let's consider two cases. Remember, Px has a variable computation time. So let's take the case when Px takes time 35, which is the longest time it could take. So what might happen is the following. P1 comes, gets the CPU, because it's higher priority, it finishes at time 10, sends a message over the network, P2, Px starts, Px takes 35 time, meanwhile P3 starts running, P3 has the computation time of 30 or whatever, right? Yeah, 30, so it finishes at time 40, and then P2 finishes at time 45, sends a message, P2 runs, everything is good because P3 was able to finish in time 30, right? So far so good. Let's imagine now that, as luck would have it, Px actually, in this particular run, Px only takes time 25. So now what will happen is that again P1 runs, then Px starts, P3 starts running, but now Px finishes quickly, so it finishes at time 35. It sends a message on processing element 1. Now P2 becomes higher priority because P2 has the data that it was waiting for from Px. So P2 gets the CPU, so P3 hasn't yet finished, it only got 25 units of CPU time, and so P3 in this case finishes at time 50. And so the interesting thing out here is that something ran faster and my system missed the deadline, right? I mean, that's kind of the non-intuitive thing. Generally, you would say, okay, if something runs faster, then I'm only kind of better off. So now you can imagine cases like, let's say Px was not variable time. I designed a system, Px, and designed the system, and Px had 35 units of time, and everything is fine working. And then I replaced this processing element 2 by a faster processor. That sounds very like, why should replacing a CPU with a faster CPU suddenly make the system miss a deadline? But that's exactly what will happen out here, right? So the challenging aspect that we face in this multiple processor kind of scenario is that things that you would expect will improve things may actually end up causing a miss of the deadline. And the reason, therefore, it's NP hard is because you have to exhaustively test for all possible scenarios. I can't simply simulate assuming Px took the longest period. I have to simulate for every possibility before I can declare that it will work. And so the simple question of, is a proposed partitioning, a proposed mapping of task to software, does that work? Answer really is you'll have to exhaustively test for it. Okay, so that makes kind of things challenging. Yeah.
So in the lower case, Px is 25, and the case doesn't work?
It doesn't, right? Because Px25 sends a message, and so now P2, which is higher priority, is able to run. So P3 is delayed.
Right. Oh, okay. Right.
Right?
PC wouldn't be finished by the time.
Right. So P3 is going to finish at time 50 now, which causes the missing deadline.
Can P1 just wait for PC to finish then?
Well, if P1, you mean P1 waits for Px to finish?
Yeah.
Well, firstly, now you are outside the world, outside the domain of the way static scheduling works. Remember, the static scheduling was that if there is a process which is ready to run, then I'll give the CPU to that. So what you are arriving at is kind of a very interesting question, which is, should I always run? If there is a task ready to run, should I run it or should I wait? Now, these kind of schedulers, which if there is a task ready to run and I'm therefore going to run it, are called as work conserving schedulers. Work conserving. Basically what they say is, if the CPU is free and if someone can use it, I'm going to use it. There are also schedulers called non-work conserving. And they precisely try to do what you are implying, which is maybe look ahead. So if I have a task, and if I give to it, it's going to hog the CPU for a long time. So let me be careful, because I know something more urgent is going to arrive very soon. So I'm going to let the CPU idle. Okay. Now, unfortunately, in this case, that wouldn't have helped, because if P3 has arrived, and so if I wait, then it will also miss. But in some
P2 also have higher priority.
P2 has higher priority, so P2 runs. So the thing is, while your scheme won't work, there are certain scenarios where you could imagine deliberately leaving the CPU idle for a bit can help, but you have to be able to say something about the future in order to be able to do it. And those schedulers are called non-work conserving. Very rare, but they do exist. Okay, and again, the intuition is it's kind of like reserving table in a restaurant for a rich person who's going to come, right? So you go there, table is empty, but the restaurant is not going to give to you because there is some higher utility task which is anticipated to come. Okay, so you could imagine those kind of things. Here, you could think about some different scheduler which can maybe solve these kind of issues. But the scheduling strategies we have discussed thus far do not fit are going to run into these challenges. And so there are in multiprocessor setting, there are a whole bunch of anomalies like these that arise, and essentially the essence of this kind of very old theorem is the following: that in a multiprocessor setting, measures you do which you might think are going to improve things, like reducing execution time, like removing dependencies, etc., may actually end up causing an increase in the length of the schedule, that is the response time. So one has to be careful, therefore, in the multiprocessor setting, that there are counterintuitive implications there. I have this slide which basically shows some of them. So let's imagine starting out, I had a set of tasks which look like this. So there are 9 tasks, I think, out here, and these arrows mean data dependency. So like J1 feeds into J9 and so on and so forth, and then these parenthetical things are the execution time. And I'm not going to go through the details, but what I'm trying to show out here is that initially I had an optimum schedule. Don't ask me how we came up with that, but which looks like this, okay? And what I'm going to do is, one by one, I'm going to attempt to improve things, but you will see that they actually backfire. So for example, I add one more processor. Previously I had 3 processors, I add 4 processors, okay? And I attempt to use all 4, okay, because they are free, so I'm going to, and in that case, it turns out that the length of the schedule goes up, okay? Now, of course, this would be the equivalent of saying, even if I have 4 processors, in this case, I would have been better off not using one of them, okay, and then I would have achieved this. This particular if I were to reduce execution time of each one of the tasks by 1 time unit, right? So each of the assigned tasks, the execution time is reduced by 1 time unit. You would say, great, I mean, that should only help me for the deadline. Turns out, again, the length of the schedule increases because of the way the priorities end up interacting. You might say, hey, what if I were to remove some of the edges, some of the dependencies? That gives me more flexibility. Things can only become better. Again, turns out that's not the case. So the challenging thing out here is that in these situations, again, that things you might think intuitively would only cause the deadline to improve may actually not act that way. So the multiprocessor case is a can of worms, and not only the design is difficult, but verification is difficult. Okay, so that's the challenge that you end up facing. Final bit, non-preemptive scheduling. So thus far, if you think about it, all the theory that we developed assumed that I can bump off the process which is currently running at any time. As soon as something higher priority is ready, I'm going to run that. And we kind of ignored that, oh, we can't really stop things in the middle of a clock cycle, middle of an instruction, but barring that slight quantization issue, basically the models that as soon as the current instruction finishes, we're going to bump it off, and we kind of made all the assumptions about that the operating system takes 0 time to do this context switch and all. But what if I cannot bump off a currently running task? What if that task has to voluntarily give up the CPU, as in maybe it makes a call to await, or maybe it asks for a resource, so it has to give an opportunity. I cannot just bump it off arbitrarily, but only when it makes some sort of a system call. So in those cases, it's called non-preemptive scheduling. Now, there are many situations where non-preemptive scheduling is very natural. So non-preemption is very common in communication systems. So let's imagine, thus far we've been talking in terms of CPUs and computation tasks, but let's say my tasks were sending packet over a radio or over Ethernet. Unfortunately, with communication systems, if I'm sending a packet, I can't simply stop the packet in the middle and restart from where I left off. I have to restart from scratch, from the beginning. So if I'm sending a 1,000-byte packet, and if at byte number 400 a more important client came in, and I want to give the link to that client, sure, I can go ahead, but next, when I restart, I have to restart from the beginning, as opposed to restarting from where we left off. And why do you think that's the case? Why can I not restart transmission of a packet on a communication link from where I previously left off?
There's no buffer.
No, the order
Packets have headers and all the information.
Yeah, the sender doesn't.
Yeah, well, so part of if you recall, when we were talking about serial communication, I was talking about how clocks are synchronized and all.
Yeah.
All of that is lost, right? Because that was only valid for some duration. So, so I'll have to send a new header and all. I'll have to develop some sort of a protocol. The other thing is that when you stop the packet in the middle, then you still have to send some sort of error correcting code and all. So it's just generally a huge pain to be able to stop the packet in the middle and restart. You have to think a lot more carefully. It's not simply let me save all the registers and restart from there. Okay, there is a lot more need to be done. So usually, I mean, almost like 90. I don't think I know of any communication system where you can do that kind of restart. I guess in principle you could perhaps develop something to do it, but it would be pretty high overhead. There are a lot of other things like that, right? I mean, let's say I have cameras, and multiple applications can use those cameras. And so if a camera is, if I'm going to take an image from the camera, let's say it involves moving the camera into the right direction, setting the zoom to the right level, taking the image, then coming back. So let's say I started doing it, and then lo and behold, some more important client comes in, and I'm preempted. Well, next time around, I have to kind of again do all that setup procedure all over again, because that is lost. So, so many systems are intrinsically non-preemptible, and so you face non-preemptive scheduling there. On the other hand, non-preemptive scheduling has a big advantage. I have less state to store because I'm not arbitrarily interrupting the existing thing. Okay, so it's a lower cost process if I can pull it off. But yet we don't see it as much as you might imagine. There are a couple of things. Firstly, non-preemption does suffer from the issue that I had articulated previously. That is, what about a rare but long-running task? So let's say I have something which comes once in a blue moon, but when it comes, it's a CPU-bound task, doesn't need any I/O, and it needs a minute of CPU time. Well, I'm then going to be stuck behind it. Okay, so non-preemptive, generally speaking, is going to be not able to schedule certain kind of tasks which preemptive could, despite the extra overhead that preemptive things place. The other thing is that the theory for non-preemptive is much harder, much more difficult. It turns out, contrary to what one might start out thinking, it's actually a lot easier to analyze the preemptive situation, and that's why the theory is a lot more developed than in case of than in the case of non-preemptive. Non-preemptive has another advantage. Since the application knows when it is grabbing or not grabbing, grabbing a resource and releasing a resource, we don't have to worry about all that issues with deadlocks and semaphores and stuff like that, because no one else can interfere with that process. So non-preemptive, again, a lot of things become simpler, but analysis becomes harder and the performance becomes worse. So that's kind of a trade-off that you face. But so we don't see it as much, but there are some variants of non-preemptive where there are good theoretical results at this point, and in particular, the scheduling strategy that works out well is something called earliest deadline first. And we're going to see that shortly in a different context. I'm not going to go into any detailed results on non-preemptive other than to kind of point out that things become a little bit trickier when you have non-preemptive stuff. Many of the older operating systems were like that. Like if you go back to original early versions of Windows and Mac OS, they were all non-preemptive. That is, or often the term used was cooperative scheduling. But basically, the idea was that the operating system will get control only when the application gave it control, as in only when the application tried to make an OS call. So you could have these situations where, and if the process, if the task is doing some long running computation, then your whole system froze. So the guidelines, I mean, I recall kind of this is pre Mac OS XX, kind of the original Mac OS. So they would have guidelines like the application must quite frequently put calls to the operating system. And there was a call to the operating system which basically said, hey, I yield to you, I don't have anything to do, but go ahead and just check whether you want to do something. So you would see those older applications written where in the middle of the computation you would have yield, and the yield basically gave control back to the OS so that if there was something more important, waiting could be done. Okay, now as you might imagine, that's kind of ugly code because making a lot of assumptions about how much time has transpired and all, but that's how you had to do things. Now with preemption, you don't need to do it because if the OS has something more important to do, it can stop you from doing it. It can stop you and do that. So the final bit is what happens as we move beyond static priorities. Some of the limitations that we have seen thus far become easier when priorities can be dynamic. We saw dynamic priorities a little bit. Where do you recall where did we have the notion of priorities of a task being dynamically altered? Last lecture. Where? Shared resources, priority ceiling protocols. Remember in priority ceiling protocols, when we were going after shared resources, then the resources themselves set priorities, and so that's how we were dealing with that whole issue of a low priority process kind of dealing with it. So we already saw the notion of dynamic priority, but dynamic priority buys us a lot. So I see that we are at 5:03, so let's take a 5-minute break and then pick this thread up. Oh, one other thing I wanted to say was that Thursday's lecture is going to be by a student of mine who's going to talk about Android OS architecture and how to write Android apps. Part of the reason we do it is, I mean, it's obviously a great example of a embedded-ish OS, but also some of your projects involve writing things, and I know like you haven't been exposed to it, so that will be a good intro to how to start. Like if your project involves writing an Android app with sensors and all, then that would be good. Okay, so anyway, let's take our break and then continue.
Yeah, three. No, the homework is separate from the documentation. Yeah, it's like one of those. Problem set is just like, let's just push. Yeah. Yeah. Like basically, there's a thing to do actually. It's in the Piazza and the resources. You can like look up the lecture slides. You post them actually before the lecture. Like on Tuesday.
First 2 weeks I was like,
The other classes like
great way of doing it. What about you? What's up? You start phone? Yeah, I was trying to get started on phone for today, so I had no choice. I did a little bit of work in my other classes.
Yeah, all the things confused.
Yeah, not surprised.
Yeah.
Yeah, I mean, all these massively produced copies, like, overtoast or over roasted and stuff.
Yeah, it's true.
Then you lose all the flavor.
Yeah, that makes sense. Like his cat basically like put some associated signals together. Yeah, no, that's nice. No, I think it's in the plan.
Really?
Yeah, I think so.
I mean, they use the C's times, so I think that would have to be a part of like the school. Applied sciences and engineering.
Yeah.
Yeah. That is kind of weird.
Okay, let's restart. So, um, so thus far, as I mentioned, we saw static priority and we saw dynamic priority in just specific context of resource sharing, where if a resource was being used by a higher priority thing, then resource was needed by a high priority task, but was locked by a low priority task, then we would bump up the priority of the low priority task. And so we saw them as part of the priority ceiling protocols. But it turns out that dynamic priority are useful otherwise also. Intuitively speaking, you might imagine that one of the notions of priorities may be driven by a sense of urgency, right? I mean, I may have a deadline which is far out, then I'm going to the system is going to give me less priority than someone whose deadline is closer. And we often see that in real life, right? I mean, if your flight is closer to departure, then they make you cut through the queues, for example, right? So this intuitively, that notion kind of makes sense. It gets formalized under a couple of varieties of dynamic priority systems that you see. One is called earliest deadline first, and kind of the idea is the following. So remember, thus far we saw rate monotonic or deadline monotonic, but they really focused on the relative deadline. They basically said that whosoever has a smaller relative deadline gets the higher priority, and that we can know a priori, right? I mean, the moment a task is declared, we know its relative deadline. The earliest deadline first is really referring to the earliest absolute deadline, kind of like if I were to mark out the deadlines on a time scale, UTC, let's say, and now I'll say, okay, task 1 has a deadline of 5 p.m., task 2 has a deadline of 5:02 p.m., and so on and so forth. And now we are talking about which one has the earliest deadline on that time scale. So you can also think of it as least time to go. And what may happen is that if an event occurs, maybe an external event, maybe one of the currently running tasks generates an event, then that may activate some currently waiting task, and now that task may jump ahead. Okay, so the priority ordering can change now, right? Because a new event may arrive, and then suddenly a task it may go somewhere in the middle of the queue. Yeah. So the OS has to kind of maintain some sort of a queue sorted by this wall clock deadline. Okay, and every time an event happens and causes a task to become ready, then I have to kind of insert it into the queue someplace. What is such a queue called? Data structure courses. Anyone? Priority queue. Yeah. Easy name, right? Priority queue. So what's the disadvantage of priority queue?
Sorting overhead on it?
Yeah, or rather insertion overhead, right? I mean, so you have to kind of figure out where to insert, right? You can't just insert it in the back as you would in a normal queue. Okay, so if you have lots and lots of elements, then that can be a challenge. If you only have a small number of tasks and all, no big deal. I mean, you can just do a linear sort or organize it at some sort of tree structure to do it. So there are good data structures and all. One of the challenge is that that a situation where you encounter large queues are switches in network where lots of packets and they need to be sorted in this particular manner. And so you need to be able to implement these things in hardware because I mean, these are things running at gigabits or tens of gigabits per second. So implementing EDF in certain situations can be tricky. The other one, which is not as well used but essentially performs as well in terms of the guarantees it makes, is called least laxity first. So laxity refers to the difference between how far away your deadline is and how much computation time I need. So it's taking both into account as opposed to simply how far away my deadline is now to one which is what's the gap. So if my deadline is 5 hours into the future, but I need to do 4 hours, 59 minutes of computation, then I am higher priority than someone who needs to do 1 minute but has a closer deadline. Okay, that's kind of the intuition. So least laxity first. It has a large overhead because it causes more changes in priority, it turns out, but so it's not sort of, you won't see it analyzed much and all, but it exists. So there are operating system kernels which implement EDF. They are rarer. You won't find them in the usual embedded OS or general purpose OSs, but there are. There are a couple. There's one called Shark and one called Erica. They are all kind of open source, so they're kind of available. I think some months ago I saw that Shark was being implemented on Embed also, but but anyway, they exist. So the one which you will more likely encounter is EDF, both preemptive and non-preemptive versions of it. In communication systems like switches and all, it would be non-preemptive EDF. In case of CPUs, it would be preemptive or EDF. But as kind of we just discussed, the idea is that I'm going to maintain the tasks sorted by their wall clock deadline, and then anytime I have to pick anytime the deadline of the front of the queue is sooner than the deadline of the one which is currently running on the processor, I bump off and start running this. That's kind of the basic intuition. So in this example, depending upon the arrival time, I may have different apps, the different deadlines. So like for example, arrival time 0, 4 and 5, some execution time, the absolute deadline. Okay, so not relative anymore. So the absolute deadline is the earliest for so what will happen in this case? When I start out at t1 equal to 0, arrival time task 1 has arrived. It's the only task in the system, so it will have the highest priority. So it will start running. Then at time 4, t2 will arrive, and t2's deadline is 10, 10 whatever on the wall clock. So now it becomes the higher priority. So we will give the CPU to that. And then at 5, T3 arrives, its wall clock deadline is 25, so it's out in the future. So T2 still gets to run. T2 will run from 4 through 7 because it's 3 time units. At 7, T2 is finished. Now T5 gets to run because its wall clock deadline is sooner. So from 7 through 17, T3 will run, and then from 17 through 23, T1 will run because T1 had already used up 4 units of computation time. So that's kind of what will happen out here. Now, the main result without is EDF is the best. Okay, and what do I mean by that? EDF is the best among all preemptive scheduling algorithms. Okay, for following situations where we have one-shot independent tasks with given arrival times. So that is, I have non-periodic tasks, but I know the arrival time of the task. Those situations, as well as if I have independent periodic tasks with Ti equal to Di, which was the same situation we have with rate when we started discussing rate monotonics. If a set of tasks, periodic tasks, with their relative deadline equal to the period, then EDF is optimum in the sense that if any algorithm can schedule that collection of tasks, then EDF can also. So now remember, in rate monotonic, we often entered into situations where there was excess CPU capacity, but we were still missing the deadline, right? I mean, we had all those rules about like what should the processor utilization be and all. The rule for EDF is very simple. If I give you a set of tasks TCD with their values of TC and D, and then T equal to D, then as long as utilization is less than equal to 1, it can be scheduled. Okay, and of course if utilization is greater than 1, then I really don't have a choice. I just have to get a faster processor. So EDF is great in this regard, that if it can be scheduled, then it can schedule it for you. Okay. It turns out though, unfortunately, excuse me, that there is no easy schedulability test if relative deadlines are not equal to periods. So outside this case of Ti equal to Ti, if Ti is not equal to Ti, then you essentially again have to do kind of like a simulation of sorts. and also for the multiprocessor case. But in a very commonly encountered case of periodic tasks with deadline equal to period, yeah, thing is simple. Okay, just add up their utilization, and if the utilization is less than 1, then good to go with EDF. It's the same schedulability test which also works for least laxity first. Same thing, utilization less than equal to 1, so it too is optimum, but less used. So if something can schedule it, so can EDF. Yeah.
So we've been saying that like whenever we have like a system of multiple processors, it's just in general harder to schedule. Does that also extend to like a processor having several cores?
Yeah, it's a multiprocessor. Okay. Exactly. Yeah. So extend to
so
say.
like hardware built in to like help with the
Anytime you have
cores.
multiple schedulers running, then things are like that. Yeah.
But then can I also say that if I have multiple processors, then scheduling is not that important?
No.
No, you can't. Why do you say that?
Because I have like equivalent of multiple threads running in this.
No, you're saying because I have excess resources?
Yeah.
Yeah. So look, okay. So firstly, yes, if you take that argument to the extreme, kind of a ridiculous extreme of sorts, then of course you are true, right? I mean, I can have a processor per task. Every task is the highest priority task on its processor, sure. But even then, if the tasks are interdependent in any form, you again have to worry about that issue, right? But presumably, as good engineers, we do care about cost, right? And therefore, amount of resources. I mean, engineering is always about meeting goals under some constraints. If you take away the constraints, life becomes far less interesting, and of course, your company will not make profit. So, lots of issues there. Slight issues, but you will not get rich from your stock options. And all the consequences that come from it. Okay, so anyway, yeah, so I mean, that's the equivalent there would be saying, if I keep utilization below 0.69 and use rate monotonic, I'm good to go. If the tasks are independent and all, surely. But again, we saw there were a lot of other confounders in the picture anyway, okay? One place where you do end up with one processor, one task is when you are making a custom chip, right? I mean, there oftentimes we just, when we say hardwire an algorithm, what we are really saying is that I have a dedicated processor just for that algorithm, okay? But even there, when things interact, bad things happen, okay? So it's not a panacea, but yeah. Okay, so the EDF schedulability test in case of di equal to ti is simple. What happens when that is not the case? So I'm going to attempt to give you the intuition behind the way the test proceeds, okay, with hand waving over some of the underlying math to then kind of give you the final recipe, okay. So the basic idea is the following, that we look at how much demand is there for a processor time over a time interval. So let's imagine that we are looking at two time instances, T1 and T2. And what we are going to do is we are going to compute how much demand was there for the processor during that time interval, okay? So what in effect I need to find out is, during that time, how many instances of a task would be there. So if I'm looking at kind of task I, and these were the different instances that came. If I'm looking at this period T1 through T2, then I have to consider all the instances that are falling within it, as well as things which are partially falling within that, and likewise there might be things which are partially out there. To be able to do this, I have to know a whole bunch of things, right? I have to know what is the period of the task. I have to know when the first instance of the task arrived, because depending upon when the first instance of this task arrived, I may have such an overlap situation or not. So it turns out that the expression that gives us the number of instances that are going to execute in an interval t1, t2 kind of looks like this, and intuitively what it is doing is it's basically counting how many periods lie within it, and then the ceiling and floor follow to kind of get the complete task. From that, in the situation where all the tasks arrived, the first instance of the task arrived at t equal to 0, so that means that the phi I was 0, then I can basically now define, I can look at the interval from t equal to 0 through some L. So I'm basically saying from 0 to L, how many instances of the task I arrived that I have to account for. That's the load on the processor. And the load on the processor looks like this. Okay, so it obviously depends upon how much is L, but it also depends upon Ti, Di. Okay, so that's we put all of that out here. With that, I can now sum over all the tasks. So this is number of instances. I multiply it by the computation time of the task and sum it over all the tasks. Then I get, let me just fix this thing a little bit. Okay, so little g 0 comma L basically tells me through this equation that what's the total computation demand that existed on the processor during a time 0 through some uppercase L. And then it turns out that the schedulability test basically boils down to saying that the demand on the processor should be less than the time that was available, which was L. So basically we are saying in 0 to L, the total computation demand should be less than equal to L, because if it wasn't the case, then the deadline would be missed. And that should hold true for every possible value of L. So essentially saying, starting from t equal to 0, if I look at every time horizon, what should remain true is that in that time interval, the total demand that came from all the tasks that could have arrived is less than equal to the time that was available, which was L itself. Okay, so that's our basic test. Now, of course, I could work with this thing for values of L from 0 to infinity, but that's not a very useful test. So the question then becomes, can I translate that into a simpler test? Just give me a sec. I just realized that. Okay, so I could do this test, but again, doing it for all values of L doesn't make sense, so not a very useful test. So we are going to simplify it. Now, looking at the particular case of period equal to deadline, remember that was the test for which we were doing the simpler case. So in that case, it turns out that this test for all L that demand is less than equal to L is equivalent to U less than equal to 1. Okay, and there is a proof step for both ways, but I'm not going to walk through it. But this is where the EDF schedulability followed. So for the case of deadline equal to period, that every time horizon demand is less than equal to available time translates into saying that load on the processor is less than equal to 1. And just playing with some ceilings and floors, and one can show that. So the more interesting or more difficult case is when, excuse me, uh, when we are looking at kind of the more general case of TIs and DIs. So essentially the goal then is, can I simplify this equation so that I can test its validity without having to exhaustively test for every possible L. So a couple of observations, that if tasks are periodic and simultaneously activated at t equal to 0, then the schedule repeats itself at every hyperperiod h, where h is essentially the LCM of the period. So essentially I only have to check for L less than equal to h. Okay, I don't have to truly do it all the way to infinity. Observation 2, this function g0L is a step function which increases only when L crosses one of the deadlines. Remember, okay, so essentially every time if the intuition out here is that we are going to look at certain interesting points, and if we look at what time instance these things are changing, then there are only certain time steps where G0L changes, and we can therefore focus on just those change points. And in particular, the demand only needs to be verified when the absolute deadline values are met. So what it boils down to is, as a consequence of this, I'm sort of again skipping over, just give me a sec. Okay, so when L crosses those transition points, those are the only places we have to check. And the final simplification that we have to do is that we can observe that the ceiling is less than equal to the number without the ceiling. And so now what we do is we define another variable, uppercase g, where we don't have the ceiling function, and we kind of simplify this thing, and it becomes like a straight line. So essentially, I had the original little g, which is a demand function, and now I have an upper bound on it, which is this uppercase g, which is following from replacing the ceiling without the ceiling. And it's linear in L, because if you simplify the expression, it kind of becomes some term out here plus L times u. So, so for all L greater than equal to 0, this stepwise function g is less than equal to this linear term, which we can calculate easily, right? I mean, as a function of L, I know TIs, DIs, UI I can compute, and so on and so forth. So the situation we have is kind of like the following. I have a line which is my upper bound on the demand function. I have the actual demand function, which is the stepwise thing. And as we kind of pointed out, I only need to check them at these transition points, which correspond to the absolute deadlines. And remember, what was my goal? My goal was that I wanted to make sure that this G0L, little g, is less than equal to L equal to T, which is the demand GL less than equal to L, right? So I want to check it's lower than this 45-degree line. So what it says is that if I look at the intersection of L equal to T with the uppercase g, let's call it L star, then higher than L star, big G is less than L, and therefore little g is, and we know little g is less than equal to big G, therefore we know little g is going to be less than L. So beyond L star, we know that the processor demand constraint is going to be met. So I only need to check until L star. And I only need to check at these absolute deadlines. So essentially, what started out as, oh, is little g less than equal to L for all L, we simplified it into, I only need to check until L star. And L star is nothing but the solution to big G equal to L. And I only need to check, even within this, only need to check at the certain deadline points. So now it becomes kind of a much simpler enumeratable problem. So in essence, the constraint basically boils down to that checking that expression for all values of absolute deadline. So you're going to enumerate all the absolute deadlines that will occur for values which are less than equal to L star, which is very easy to compute, and H, which is the LCM, so kind of a smaller of the two, and within that only at these particular values. And L star is kind of just a simple algebraic equation. So this continuous constraint, continuous expression, which was over all time greater than equal to 0, is now reduced to just a set of finite checks. So to give you an example, let's say I had this task set. CIs, DIs, TIs are given to us. Then we can compute U. U is 11 over 12. But since deadlines are not equal to period, if deadlines were equal to period, I would have said, great, we are done. Okay. But since deadlines are not equal to period, I have to do this more exhaustive test. So I calculate L star by plugging in this data. L star comes out to be 25. I calculate hyperperiod, which comes out to be 72. Smaller of the two is 25. That means I only need to check up to 25, and I only need to check where the absolute deadlines were happening. Now, what are the absolute deadlines of T1, task 1? 4, because it arrives initially and has a deadline of 4. Then next it arrives at 6, will have a deadline of 10, and so on and so forth. So we can enumerate all the possible deadlines that are there, and those are the values where I'm going to check. And so I compute the little g at those places, and then compare it and see whether it is less than L. So in this particular case, I think every little g is less than L. And the other thing you can see is that at this place, at L equal to 16, the little g is 16. That means if I were to look at the time horizon 0 through 16, then the demand on the processor was 16, and I had 16 time units available. So the processor is just the right speed. If I were to slow down the processor even a teeny bit, then the deadline would have missed, right? Because if I slowed down the processor, little g will go up, so this will exceed. So even though in this case processor utilization is only 11 over 12, there is no slack in the system, right? I can just barely schedule it. Whereas on the other hand, if deadlines were equal to period, then that would have meant I could have slowed down the processor by 12 over 11 and still be okay with it. Okay, so the shorter deadline is constraining the thing a little bit more. Okay, so EDF again. So EDF deadline equal to period, pretty simple. Just calculate U less than equal to 1. You're good to go. Deadline greater than, deadline less than period. Then you have to do this kind of analysis to make sure. And this notion you'll find again and again in other scheduling algorithms, if you were to do in literature, that this concept of processor demand, that something is schedulable if for every time in period I can make the claim that the demand on the processor was less than equal to the time available. Because intuitively speaking, if demand over any time interval is less than equal to time available, then that's the definition of schedulability. Okay, so that's EDF. RM versus EDF. So I mentioned that EDF is rarer in the operating systems, and most of it really has to do with the complexity involved. Okay, in the sense that the priorities can change dynamically and all, so that kind of becomes a more complicated thing to do. The same kind of issues that we encountered in static priority encounter here when it comes to shared resources. So what happens if a task whose deadline is very close needs a resource which has been locked by a task whose deadline is quite far away? That is equivalent to what we encountered when we had the priority inversion scenario. So here, again, similar things happen, which is temporarily we will try to give the task whose deadline is actually quite far away higher priority because it is locking nearby priority task. So fixed priority is simpler to implement because you don't need those priority queues and stuff like that. But if you only have a small number of tasks, it's not a big deal. It's only when you're looking at systems with hundreds or thousands of tasks that complexity comes into play. EDF has the same issue as priority inversion, and otherwise EDF actually has some pretty nice advantages. In particular, it's very graceful when it fails. So what I mean by that is, so firstly, EDF, as we saw, is able to utilize more of the processor. So you can, for same set of tasks, if you are using EDF, you can get away with a slower processor, which translates into lower power or a cheaper processor. So that's an advantage. The other thing is that remember, for static priority, I had said what happened was that if the processor slows down, or if effectively I have less computing available, then the lowest priority task misses the deadline. In EDF, the behavior is kind of different. The behavior is as if everyone kind of suffers equally. So it's kind of a fairer way of penalizing things when things start going bad. So you'll find EDF quite a bit in networking and these kind of situations because the resources are very precious there. But even on CPU side, there are some OSs that kind of provide that. So EDF, and then there is non-preemptive EDF, which is this is just a repeat. Non-preemptive EDF. So going back to our preemptive thing, it turns out non-preemptive EDF. So non-preemptive EDF, what would happen is when the task voluntarily gives up the CPU, at that time we are again going to select according to the EDF criterion. So as opposed to preemptive EDF, which is what we discussed thus far, in non-preemptive EDF we do that. It turns out non-preemptive EDF within the world of non-preemptive schedulers has optimality criterion. So this is a table which kind of shows in a non-preemptive setting what role non-preemptive EDF plays. So let me explain this table. So set of periodic tasks versus set of sporadic tasks, non-periodic tasks, okay, where we only, okay, set of tasks where we don't know when the first task arrived, and then there is a concept of concrete task where we know when the first task arrived so that we can predict upfront when every following task will arrive. It turns out that whenever we can solve the problem, non-preemptive EDF is the optimum. And one corner, which is periodic task and set of concrete tasks, which is I knew when the first instance arrived, that one we do not have a polynomial time algorithm, okay, unless we put it. So long story short, EDF is kind of like holds, it's kind of the nice one to have whether we are looking at preemptive cases or we are looking at non-preemptive cases. So it's kind of like intuitively the best you could achieve, implementation cost aside. And the implementation challenge is that most operating systems that you will encounter for CPUs are support static priority with either preemptive or non-preemptive. One of the homework question asks you is that is the embed OS preemptive or non-preemptive? So I want you to take a look at it and find out. These are very simple questions, but just go and see whether it is preemptive or non-preemptive. Okay, Linux is preemptive, although it is not EDF. Linux uses some other schedulers. There are a lot of other RTOSes and all which use preemptive one. So just find out what embed does. Is it preemptive, non-preemptive? It is priority based, so that it certainly does have. So anyway, I'm going to stop out here. So next lecture again is I'm going to be here. It's going to be by my student Mustafa. So he's going to walk us through Android and both kind of Android OS architecture. I think it's kind of interesting. It has some interesting features, as well as what does an Android app look like, and also those of you who need it would at least have a starting point. So see you on Thursday.
For the framework, you want like type solutions or
You can, I mean, I strongly prefer typed one because so what I would basically suggest is that just make a copy of the Google Doc and just type in there, right? Yeah, that's the easiest way. Now, I don't know how many of you have used Gradescope, if anyone, before? Okay, a few knows. Okay. If you run into a problem, ask question on Piazza, but basically the way Gradescope works, those who have not used it, you upload a PDF file with your solutions, and then you go through a phase where for each problem you are going to designate which page in your PDF it exists. And I'm yet to create that question rubric, so you can't do it today, but within the next day or two I would have that running. So basically I would have a list of what the questions are or each subpart, and you will have to do that mapping. Okay. If you do handwrite something, you can, and you scan the PDF and you upload it. So that's certainly doable, but it's just type it in. I think it's a lot cleaner. So. A week from tonight. Okay, and basically you can take 25% per day penalty for it, which means up to 4 days. So I would not recommend it, but